This meeting is being recorded.
Yay.
Okay, so do you have any questions before you get started?
I don't think so. I think we're good. Okay.
Okay, well then whenever you're ready, go ahead.
Okay. I think we're starting with. Okay, wait.
Let me. What happened? There we go. Share. Moon is what you want to start with?
Yeah.
Okay.
I'm sorry, just really quick. How long do you anticipate your each presentation? Or do you have just one, or do you have two separate? Looks like you have two separate ones. Okay. Right, go ahead. You got to unmute yourself though.
Oh, okay. So it is not letting us have audio and share the screen at the same time. So as soon as we shared the screen, it muted us and it said we could not have our audio and our screen shared simultaneously.
I think you can try just screen sharing the whole window instead of a tab, maybe. Wait, go to like entire screen and try that maybe. Does that work? Hello?
Can you still hear us?
I can hear you.
Okay, we'll try it that way then. All right.
Okay. Okay. So this is our Moon 101 presentation by Alexis, me, and Cameron. Okay. And we're starting with the first image. And in this image, we identified three features. We identified simple craters, which are circled in yellow, complex craters, which are circled in blue, and then mare. And we showed the light coming from the left because with all the little craters in the image, you see the shadow coming from the left side and the light reflecting from the right. And so that kind of indicated to us like where the light's coming from. And we also found the Apollo 12 landing site near these two craters over here. And then for geologic features and formation, for simple craters, we have that they're formed by an impact of a foreign object that displaces material and then ejects it in all directions, which forms a bowl-shaped indent and a buildup of material around the rim. And for complex craters, they're also formed by impact, but the materials rebound to form a central peak in the middle. And their walls are also sometimes collapsed or terraced. And then the mare, which is all the dark spots on the moon, is the remnants of a vast lava flow that leaked onto the surface billions of years ago. And then for relativity, for the impact craters, we have the brightness of the ejecta blankets. So the ejecta blankets with more white around the rim are likely younger than the ones that don't have very pronounced rims. The roundness, like the rounder, more dull the crater, the older it is. And when compared to like others that have more sharper features. And then for superposition, all the little craters that are found like on top of these big craters are all younger than the craters that they're on top of. And then for the relativity of mare, we said that it was around 3.16 to 4.2 billion years old. And that's it for image 1.
And then for image 2, we have identified the rill as the Hadley rill. We also identified that the light is also coming from the left in this image. The landing site we have found up here, which is the Apollo 15 landing site, which happened July 30th, 1971. We also found one complex crater in this image from what we've seen and zoomed in on. But there are a lot of more simple craters around. And then this light spot we have identified as the ejecta blanket of St. George crater and the Apennine front. We have some better visuals, as you can see here. Here is the actual image and the St. George crater that we have identified. Some geological formations that we have found were simple and complex craters. It's basically the same explanation before, but we have also found an elongated crater, we believe, right here. We have started as well. And we have found that the Hadley Rill was sinuous, and the mare is the same as before. The relativity of it. The relativity of the craters is the ejecta blanket of St. George crater overlaps part of the Hadley Rill, indicating that is a younger formation than the rill. Also, the crater cluster towards the right of the rill is older than the other sharper looking craters toward the left of the rill. The contrast of the basin of the crater to the rim of the crater indicates how old and worn versus new and fresh the craters are. And then for the rill, the age was identified based on superpositions, and the St. George crater overlaps the Hadley Rill, indicating that it is the younger formation. This is important because the St. George crater itself is a very old formation. You can tell because of how weathered and round it is, indicating that the Hadley Rill is also very old. The Hadley Rill also has somewhat rounded edges, which also indicates that it's older. And the same goes for the mare. We still have identified them as 3.16 to 4.2 billion years old. And that's it for image 2.
All right, on to image 3. We found some simple craters, complex craters, and we have the Radley Hill circled in red. We did only find one complex crater that we could see. And then here we also have the Apennine Mountains. And over here is where the other picture was taken with the St. George crater and the Apollo landing site. We also found that the light was coming from the right because of the way that the light was hitting the mountains and the shadows. For geological feature formations, we have the lunar highlands in the mountains, which we figured out were likely formed a lot earlier than many of the other formations in the image because they're peppered with craters. And also there's the St. George crater on top of it, which is very heavily weathered. And they're also filled with feldspar-rich rocks. We also have the simple and the complex craters, the mare and the Hadley Rill, which we identified as sinuous in this picture. For relativity, we have the impact craters. Some of the older craters, like the Hadley Rill, have a lot softer features compared to some younger looking craters like these ones. The lunar highlands, as I said before, they have other younger craters on top of them, which indicates that they're older. And the rill has the St. George crater on top of it. And then that should be it for Moon 101.
Okay, great, great, very good, thank you. And actually, let's go ahead and do the asteroid presentation, and then we'll come back.
Sure.
Okay.
Okay, so for image 1, this is the Asteroid 101 presentation by all of us, as you know. We have identified this crater as the 25143 Itakaba asteroid. We have separated it into 2 lobes, as we can see. We also have identified some large boulders on it, and the light is coming from the left because of the shadow of the light. Some geological formations were the large boulders. They may be debris from impacts or large pieces from rubble held together. We also have done the lobes. 2 theories of the different lobes is possibly the 2 different shaped lobes of the asteroid may have been caused by an impact
that shattered the original parent body of the asteroid. And this may have then caused two different rubble piles to form, which then came together and accreted. Another theory is that lobes might have also been created by an impact that caused a large part of the asteroid to break off and then reattach later. Another one that we have is the craters. We couldn't identify any visible craters. That implies that the Itokawa is a rubble pile asteroid, meaning that it's not one solid rock, but rather a ball of rubble that has been drawn together by gravity. There are no visible craters because whenever an impact hits, loose debris will fall back into the hole and cover it up. And some of the relativity is the lobes. We couldn't find any way to determine the relativity of the lobes compared to the other geological formations. We know that they have formed via accretion though. And then for the boulders, we have said that the erosion wears down the older boulders and hasn't affected the younger boulders as much yet. Usually meaning the more rounded it is, the older it is, but there's no way to determine the relativity of craters because they're so micro-sized. And yeah, that's for image 1. Okay, so for image 2, we have the 4 Vesta asteroid, and we've found 3 different formations. We have the light coming up from the bottom, and for formations, we have simple craters, basins, and troughs. So for the geologic features in their formations, we have simple craters, which are caused by impacts of foreign objects, troughs, which are found along the equator of 4 Vesta and are possibly fracture lines from a serious impact that damaged the asteroid's interior. The crust, which was likely formed by the cooling of lava during the formation of the asteroid, and then basins, which are large, complex impact craters that have been heavily degraded and filled with debris over the years. And then for the relativity, the simple craters, their ages can be told through their erosion and superposition. So like certain craters on top of each other, or the sharpness or dullness of their rims and their features. The troughs, you can kind of tell that the troughs are very old formations because they're covered in a lot of craters and their features are kind of rounded, which indicates that they've been eroded over the years. And then for the crust is likely older than the rest of the features found on the asteroid, it was probably formed during the formation and accretion of the asteroid. And then for the basins, we determined that these were basins because they were a lot bigger than the other craters in the image, and they're also shallower. And as you can see, there's one basin kind of on top of the other, which indicates that one is older than the other. And the basins are also likely very old because they have been degraded and have been kind of filled in with debris over the years. Okay.
Sorry, we didn't put the laser pointer on. So the last image, we figured out that it was 433 Eros asteroid, and we found some large boulders on top of it and also some smaller boulders, and figured out that the light was from the right because of the way that it hits the boulders and the shadows. Some features that we found were, like I said, the large boulders and the crust, and the boulders were likely from impact debris, and the crust was formed from the cooling of lava. In terms of relativity, the boulders, you can determine their age compared to each other based off of like erosion. So these ones down here have a lot softer features than say these two, which have much sharper features, indicating that these ones are probably younger. And then the crust is older than the rest of the features on this picture because all of the other features are on top of it, and it's formed during the formation and accretion of the asteroid. And I think that's it.
Okay, great. Go ahead and bring the slides up. Number one, I don't like watching myself in slow motion, but also I want to. So good job overall. That was fantastic. That was great. So just some things as they come out of my head. I love how you have very little text. It's great. You the text you do have, you expanded on by just speaking, which is great. I mean, there's no point in putting text on slides that you're just going to read anyway, right? And professional scientists do that. so, so even if you had, that had been excusable because even pros do it. So I like that. I like your images and how you coded things, you colored things, and you told me you had a legend to tell me what that meant. Sometimes people forget their legends. Okay, yeah, just sticking on this slide here, but this actually applies to all the ones you have like this. When you have the word relativity, you're talking about the relative ages, right?
Yeah.
Okay, so make sure you say that. Use relative ages. Relativity is a physics term. And I don't think you want to start going into relativity questions in a lunar or asteroid project. So make sure you're real explicit that you're talking about the relative ages. And then I would even say things like, I mean, in this case, if you're saying the impact craters were the oldest, say oldest, or given a number, just something so you can tell, or say younger as you go down the list, or older as you go down the list, just some kind of cue, lets people realize what you're saying, where you're going with it. And you don't even have to say it, right? If it's on the screen, they can see that. But anyway, let's see here. Okay, let's go to that first slide from Apollo, which you're right, that is the area surrounding the Apollo 12 landing site. A lot of teams in the past typically do not catch that there is a man-made object sitting there. It's not obvious right away, but if you're looking close enough at things long enough, it'll pop out. And what's actually different about this is this particular image is actually like reversed. I took it and I flipped it around, so it's not quite as obvious. But anyway, it doesn't matter. You got it, and that's cool. I also like the baby sun. Is that from Teletubbies?
Yeah.
Okay. I thank you for the trip down memory lane, but but yes. So quick question for you: what about what you labeled here as complex craters? How are they different from the simple craters? What did you see that made you decide they were complex craters?
I think a lot of them is like we kind of zoomed in and looked at them closer. We kind of saw like shadows or like kind of like the central peak kind of thing. Like it almost looked like there was a shadow in the middle. Like there was like a rise in it. Some of them we weren't as sure on, but I think the older like rounder ones, the ones that don't have as distinct features, we knew those were going to be more simple. So I think that's what we did.
Okay, that's fair. So when you were talking and defining simple and complex, you did a great job of that. But I'll point out, or I'll ask you, so the complex craters, as you said, can have this rise in the middle, this central peak, or they can even have or these terraced walls. Or in other words, they are simply not bowl-shaped. Okay, that's another way of thinking it. In some of these that you thought were complex craters, could the things that you're seeing in the middle on the floor of those craters be something other than a central peak?
Yeah.
Okay, what else could they be?
They could be like other little craters and stuff too.
Okay.
I think potentially.
Sure. Craters on craters, craters in craters. Yeah. Any other thoughts?
Maybe there's like some wind on there, right?
Solar wind?
Yeah, solar wind. Maybe like there's some like rounded maybe boulders, I would think, or something with like a bunch of erosion on them from the solar winds. Maybe it could be that.
Okay. Both plausible. So you could have a crater in there, a smaller crater. Maybe you just can't see the whole thing, right? Because of the way that kind of sunlight angles. It could be a boulder, an ejecta, piece of ejecta from a crater nearby. That was when it was formed. Tossed a boulder right there, hole in one, right? So yeah, it could be that. Side note, so a solar wind is not a wind in the sense of we think you go outside and it's breezy. The solar wind are just these particles that constantly come off the sun. And yes, they do cause erosion. They do cause erosion, but at very, very small scales that you really can't see without a microscope. Over time, you can see a process. So you mentioned how like some of the ejecta blankets are brighter than others. Well, the reason some of them darken over time is because of the solar wind. That takes place over a long, long time scales. So a solar wind wouldn't, and the solar wind is not dense enough to actually push things, if that makes sense. So you wouldn't get the solar wind pushing boulders downhill or something like that. So yeah, either a boulder in there or another crater. So I will tell you, every crater you see in this image is a simple crater. Another thing you can look at if you're wondering, there's something called a transition diameter with impact craters. Did you read about that? I'm trying to remember if that was in the Moon 101. I don't remember. Basically,
I don't remember reading it.
Okay, it may not be. It probably should be. For every object, Moon, Earth, Mars, Venus, Mercury, any solid object with impact craters on it, there's what is called a transition diameter with craters. And basically what happens is there's a range of diameters where you start seeing simple craters end and you start seeing complex craters. And it's a bit of a range because there's a number of factors that can go into that. But basically you get complex craters, especially with terraced walls, because the gravity of the planet or the moon is pulling down on the rock, right? And so that causes it to slump. Now, the smaller the body is, the less the gravity is. So the much you can have simple craters can be much larger than they would say, like a simple crater on the moon can have a larger diameter than the largest simple craters on Earth, because the Earth's gravity is larger and will start pulling down the rock quicker. So anyway, if you look up the transition diameters for the moon, that'd be another thing. If you're wondering, you can go look at what's that. I don't remember it off the top of my head. Transition diameter for the moon, and you could measure. Since you have a scale bar here, you could measure the width of that crater and say, does it fit within that transition, or is it above or below that transition diameter? So just another thing. It's a more quantitative evaluation method of crater size. But just something to throw out there. Just go to the next slide. Okay.
Like next image or this?
Yeah, this one right here. Yeah, this is great. So you have here the for Mare age 3.16 to 4.2. What is the difference between those two numbers in terms of just numbers? What's the difference between 3.16 and 4.2 billion? Simple math.
It's by
1.4.
it's 0.04, yeah, 0.04. No, no.
1.04.
Yeah. Wait, it's not 1.0. Yeah, it is 1.04. Yeah.
0.04 billion.
Yeah, 0.04.
What's another way of saying that?
1 and 4.
You don't have to get in scientific notation. It's 40 million years.
Yeah.
Okay.
So that's a long time, right? So while saying, well, it could be between 3.16 and 4.2 billion years old, that's not really that much of a difference. Well, yeah, it is. That's 40 million years, right? So it's just one of those things to think about. when you're dealing with like deep geologic time or time scales on the solar system, especially when you're talking about the moon and you're looking back at events that happened that long ago, that even though they were right around the formation of the solar system and a billion years afterwards, 40 million years is a long time. So it's not a comment on the accuracy of the age. It's just saying that's a long time, even if it doesn't look like it is as a decimal. And then go to the Apollo 15 image, the second one.
Like the bigger one?
Yeah, the more pulled back view of it. Yeah, that one.
No. Okay.
So this is one of my favorite Apollo landing sites, if not my favorite, because as you identify, there's so much geology here to look at and so much to talk about in terms of relative age dating and just types of features. I love it. I actually love it. And I love the Apollo 15 mission. If you haven't seen it yet, you should look up Apollo 15 Hammer Feather Experiment. Have you seen that?
Yeah.
Okay.
Yeah.
Cool. Never mind. Isn't it? I love that. I love that. It's so cool. And I'm just even more impressed by the fact that, not because they're dumb, but just as somebody was like, oh, let's do this. Let's totally do this experiment. This would be so cool. I mean, I never would have thought of that, but I just thought that was, I think that's great. So you mentioned something about the mountains around here being the oldest, which they are. That's correct. But one of the points you made was because you said they're feldspathic or feldspar rocks. How does that tell you that it's the oldest? What does that have to do with those being older or oldest?
I know we had it somewhere. Like the feldspar rich rocks sort of like floated to the top of the magma ocean when like the crust and stuff was forming, something like that.
Okay.
Feldspar floated to the top as like the magma was like cooling down, so it created these like mountains, like the Lunar Highlands.
Okay.
I believe that's what it was.
Okay.
Could be wrong.
Okay. Yeah. So this rock,
dude.
when the moon formed, it was still magma. This was the less dense magma. Okay. And it flowed to the top. Those minerals flow to the top, as you said. And then they solidified and formed the original solid surface crust of the moon. And then 100 million years later, the late impacts occurred, heavy bombardment, weakened the crust. And then sometime later in those weaker spots, that's when the basalt that was lower, was more dense, more iron rich, came up, busted through the surface and filled in. So they're mountains in the sense that they are, and because when the impact occurred, that pushed that feldspar stuff up and actually raised them as mountains because of the impact itself. So yes, okay, great. Okay, in the asteroids, I just really have one thing I want to ask. Go to the second image. Yeah, for Vesta, yeah. So looking at those three larger craters there, they actually call it the snowman in Vesta. Do you think those craters formed at separate time intervals? Or do you think they could have possibly formed at the same time in a crater chain? It's like three impacts occurred simultaneously, one after the other.
I mean, I guess that they happen at the same time, just because of like they look similar to each other, maybe.
Okay. Are you sure? Because you ended that with maybe.
I don't know.
And I don't know myself. So somebody probably has a really good idea and knows why it's a crater chain or it's not. I don't know. But you see on the moon in a lot of places, or even on Mars, chains. These craters are just line up in a chain. Especially if you look around Mare Orientale, it's like a big bullseye looking on the if you're looking at the moon, it's on the left side, on the left. You can't see it from Earth, but it's there in images. You can see it. If you look just like radially, like spokes on a bike wheel, just going out from that crater, you'll just see these chains of crater formed from ejecta coming out of the basin and then forming the crater chains, what they call secondary ejecta. But anyway, okay. No, great. This is good. Have you ever presented anything like this? Some like an analysis, whether it's geologic or some other discipline?
I know I haven't. Not that I can remember.
I might have, I don't know. It would have probably been forever ago, but maybe.
Okay, well, that's fair. That's fair. No, but you did a great job. So this is good. This is really good. What was one of the more interesting? What was something you learned about the moon or asteroids that was really surprising?
I don't. Is there anything?
There might have been something, but I just can't remember it right now.
I know one thing that stumped me was when I was first starting to dig like into some of the formations and how they formed for these slides, I found out that the moon didn't have like plate tectonics like the Earth does. And so I was really confused on like the mountains and stuff.
Mm-hmm.
So I thought that was kind of fun to read into.
Very good. Very good observation or analysis or reading. So you read though it's because of the impacts, right? They're not in the traditional sense we think of as being something pushed up by plate tectonics, rather impacts, which is still tectonics, right? It's still movement of the crust. It's just not specifically plate tectonics. Yeah. Okay. Well, a few more minutes here that I actually have to get on another meeting. Do you have any thoughts of what you want to do, lunar or asteroid project?
I think me and Cameron were a little more interested in the asteroids.
Yeah.
But it's still to be determined.
Yeah, we don't know.
Well, that's fair. That's fair. It's fine. So I still need to find one more advisor. I tell myself every year I'm going to be ready by October 1st. Everybody's going to have an advisor. It never happens. But I do need one more. I already have an idea though of who I want to pair you with. But we'll wait to see who that other advisor is that I get. I might be somebody even better or make a better man. I don't know. So until then, what I would like you to do is go. So you took those two surveys one about the moon and one about asteroids. Yeah. I'll send links to take. It's the exact same thing. So go ahead and take those before you start doing anything else. And that's just a way I use to see if are you all learning some of the fundamental things I'm hoping you learn from the 101 activities. That's all we're doing. That's all I'm doing with it. So then once you've, and since Ms. Treader has done this program before, she's pretty well familiar with it, and she's done pretty darn good too. Her and her students. I mean, you can keep talking about what it is you might want to do. She can certainly guide you through that. That's something she's capable of fully. But then once you have your advisor, you can really start jumping in and thinking about things and making decisions. So I guess good luck with the rest of the program. If you have any questions, let me know. One cool thing I will mention, I don't know if Mr. Treader told you, but at the end of the year, we pick a team to go to present in person at this meeting for this NASA meeting. And we enter we enter all the posters that we send into their student poster competition, which is high school students, which are typically just you all, but sometimes there's others, undergrad and graduate students. And the winner, first, second, and third place usually gets some kind of award. I mean, they definitely get a certificate, but they usually get like money to go travel to a conference, a future conference. This past summer, the overall first place winner actually was a student from this program that won, which is pretty cool. So he's going to have funds, and he's now a freshman at the University of Maryland, but he got funds he'll be able to use to take to a conference. Well, something they're going to start doing this next summer is they're going to have like a separate kind of high school division. And so everybody will be in the overall student poster competition. But if a high school team, whether it's from this program or from another team from something else, if they don't place in the overall competition, they will automatically then be part of this high school division. And they will then look at those scores, and first, second, and third place high school teams will get money for their school, which is pretty cool. So even if you weren't to get funds for traveling to a conference, you can still get money for your school. So that's pretty cool.
And correct me if I'm wrong, they can still present regardless of if they win, correct? There's going to be a virtual way that they could present regardless.
Oh yeah. And in fact, because of that, it's making me have to kind of rethink how we're going to do our competition phase, because I still would like judges to look at your posters and give you scores and give you comments. But I don't see a lot of reason for coming up with the top 4 when anybody can present. I mean, in the past, anybody could present to you. You just had to get yourself there. But because they're definitely going to have a hybrid version or a virtual component, it's easy to attend and present. So I got to think about that, what we're going to do to come up with who we fund to send out there. I kind of thought maybe we could do like a student choice, right? Like you all decide, and you can't vote for yourself, but you would all decide. I don't know. I don't know the best way. I don't know. I'll have to figure that out. I've got some time to figure it out, but we'll come up with something. So, all right. Erin, any questions for me? Oh, I just noticed your moon on the whiteboard.
They drew that while we were trying to get into the Zoom, since we were waiting for it to let us in.
That's great. That's great.
Yeah. And we all decided to wear NASA shirts today.
Super. Very good. All right. Well, if you guys have any.
I have any questions for you. So thank you for your time. We greatly appreciate it.
Okay, well, thank you all.
Your meaningful feedback definitely helps.
Okay, good. Well, and again, good job. And when we get this posted onto the LPI YouTube channel, I'll let you all have the link.
Okay.